Hello everyone and welcome to lecture. So today what we're going to be doing is delving in a little bit deeper into the concept of what it exactly means for a Fourier series in general, an infinite series of functions to converge. And in that regard, what we'll do is actually end up defining multiple different types of convergence for infinite series of functions. The first and most basic is called pointwise convergence. The second is called uniform convergence, which is, in some sense, much nicer than pointwise convergence, and gives us all of the properties that we would expect and we want for applications for a Fourier series. The third and final type of convergence that we'll talk about is called convergence in the mean, and we'll also, mention various important ideas in regards to all of these types of convergences. Specifically, we'll talk about order of Fourier series coefficients, what's called Parseval's equation, which is a very, very important equation relating the infinite sum of the coefficients, the squares of the coefficients in the Fourier series, with the square integral of the function itself. And then lastly, we'll see Bessel's inequality, which is actually very intimately related to Parseval's equation. So the first question we want to answer, and this is kind of taking a step back a little bit, is what does it mean for an infinite series to converge in mathematics? And at the beginning, we're going to review exactly what this means mathematically. And I want to point out from the beginning that there are actually many different ways and other ways of defining convergence. So this is just what we'll be talking about is the standard way in most analysis courses, in most calculus courses, about how the convergence of an infinite series is defined. So in this regard, we'll start thinking about this following example. Let's say we have some rational number, like 1/3. We know that this number can be represented as an infinitely repeating decimal, 0.3333, so on and so forth, all the way to infinity. Now, this ... notation is not very precise, so the first way we could try and rewrite this is to say that 1/3 is equal to 3 times 10 to the negative 1, or 3 times 1/10, plus 3 times 10 to the negative 2, plus 3 times 10 to the negative 3, and so on and so forth, all the way to infinity. So this ... stands for right here. But again, this is not very mathematically precise. It's kind of a naive approach here. On the left-hand side of this equation, we have a fixed entity, a fixed rational number, and on the right-hand side we have this thing that we're calling an infinite sum. And you could ask the question, what does the ... here even mean? How do we sum infinitely many terms? How can we make sense of this? Or if we write this a little bit more compactly, this is written as the sum from n equals 1 to infinity of 3 times 10 to the negative n. But even this, you can still ask the question, what does this even mean? And what we have, and what you hopefully learned in basic Calculus 3 course, or Calculus 2 course, depending on when you talked about infinite series, is that this is understood in the sense of approximations. So we say that 1/3 is equal to the finite sum from n equals 1 to infinity, or n equals 1 to, not infinity, sorry, but capital N, of 3 times 10 to the n, 10 to the negative n, plus some error term, en, or if we write this out explicitly, this is saying that it's 3 times 10 to the negative 1 plus 3 times 10 to the negative 2 all the way up to 3 times 10 to the negative n, where we stop, and then we add some error term in. So this dot 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 here makes a lot more sense because this is a finite sum for any value of n. Which is an approximation to the exact value one-third. In this term, en, oh, and this should be e uppercase n. Same thing right here. This is the error term, which can be made as small as we like. So this is it. This is exactly what we have to go through and kind of formalize to make sense of the convergence of an infinite series. So given any infinite sequence, we denote an, which is a1, a2, so on and so forth, all the way up to an, continuing all the way to infinity. And this can be of either, we can do it with complex numbers, but we're going to be taking real numbers here. We say that an is the sum of the first n terms in the sequence, which is a1 plus a2 all the way up to an. This is a finite sum or finite series, and if we consider the new sequence, formed by these ANs, the first term being A1, the second term being A1 plus A2, third term being a1 plus a2 plus a3, and so on and so forth, all the way up to infinity. To be the sequence of partial sums. And this actually makes the idea of defining the limit of such a sequence very tractable, because we have a definitive definition from calculus on how to define the limit of a sequence. So we say that if the limit as n goes to infinity of an is equal to L, where L is some number in the real number line, on the real number line, then we say that the infinite series converges to L, where we denote the sum from n equals 1 to infinity. We use this notation to denote the limit as n goes to infinity of the sequence of partial sums. So mathematically, this is what we mean when we say that we have an infinite series that converges. Remember that the exact definition of the convergence of a sequence is all we need here. And this says that for all epsilon greater than 0, where epsilon is our error, possible error tolerance, so for any error tolerance, there exists a point in the sequence, n, and it will generally depend on epsilon, such that for all, or if n is greater than n epsilon, so we're at a point in the sequence past this n epsilon, then Sn, an, which is the nth partial sum, minus L is less than epsilon. So this is in general what it means for a sequence to have a limit. And so if that sequence is the sequence of partial sums for a given infinite series, that limit is the final sum of the series. And we know that many sequences have limits that go to positive infinity or negative infinity or just do not exist. So we also say that if the limit as n goes to infinity of an is equal to plus or minus infinity, or the limit as n goes to infinity of an just does not exist, then the infinite series is said to diverge. Or we'll just say diverges. And I want to make an important note here. There are other less restrictive types of convergence. And an example of this would be Cesaro convergence. Which is convergence in the mean. But there are other types as well, so just important to point that out. So let's get back to that original example that we started with to try to get a better feel for what this means. And so remember that we're looking at applying that previous limit definition to an, where an is the sum from n equals 1 to n of 3 times 10 to the negative n, which is just the same thing as the sum from n equals 1 to n of 3 times 1/10 to the n, which is just like 3 times 1/10 plus 3 times 1/10 squared, and so on and so forth, all the way up to 3 times 1 over 10 to the n. So this is actually a type of more general series called a finite and geometric series. We have some real number a times some real number r to the n. And we can show, and you hopefully saw this in your undergraduate Calc 2 or Calc 3 class, that this is going to be equal to, so using the basic geometric series formula, this will be a times r minus r to the n plus 1 over 1 minus r. And rewriting this using r values of a and r, you have this is going to be the sum from n equals 1 to capital N of 3 times 1/10 to the n. This will be 3 times 1/10 minus 1 over 10 to the n plus 1 over 1 minus 1/10, which after a little bit of arithmetic simplifies to 1/3 minus 1/3 times 1 over 10 to the n. And the limit of this series, because 10 to the n is going to infinity, the limit of 1 over 10 to the n is going to 0 as n goes to infinity. So this exactly shows us why 1/3 is the infinite sum of what we just expressed. If you want to get a little bit more in depth using the definition, you can say we fix some error tolerance greater than 0, and we need to find some n epsilon such that for all n greater than n epsilon, an minus 1/3 will be less than epsilon, our error tolerance. This just means that 1/3 minus 1/3 times 1/10 to the n has to be, or minus 1/3 has to be less than epsilon, which means that 1/3 times 1/10 to the n has to be less than epsilon. Which means that 1/3 times epsilon has to be less than 10 to the n, which means that n has to be greater than negative natural log of 3 times epsilon over natural log of 10. Where n epsilon here must be greater than or equal to this value. So I encourage you to go through and maybe try this out in Desmos, but this is exactly, the limit definition done out for this example. And it's a very, very good example to kind of motivate, why infinite series are very important. Now, an important point that has typically gone over again in a Calc 2 or Calc 3 course, depending on where you took Calc 2 or Calc 3, is that because the sign of the terms an is generally mixed, so this means both positive and negative terms in the sum, we actually have different types of convergence, some being stronger than others. And the strongest type of convergence is called absolute convergence. And this is if the sum of the absolute values of all the terms of the series converges. Based on the definition that we talked about before. We say that a series is conditionally convergent if the series itself converges but the series of absolute values diverges. And lastly, a series is just divergent if the sum of terms in the series does not converge. And this is a very, very big idea because it turns out that absolutely convergent is a much stronger thing than conditional convergence. So I want to note here that a given series can only be one of these three options. And I also want to note that it's possible to show that if a series is absolutely convergent, or the sum from n equals 1 to infinity of absolute values of terms in the sequence an converges, then the series itself also has to converge. So, a good example of an absolutely convergent series would be the geometric series. So with absolute value of r less than 1 is absolutely convergent. However, a good example of a conditionally convergent series would be the alternating harmonic series. This is the series of the form sum from n equals 1 to infinity of negative 1 to the n plus 1 over n, which is 1 minus 1/2 plus 1/3 minus 4th plus 1/5, and so on and so forth, is conditionally convergent. Meaning the alternating harmonic series actually does converge. This alternating harmonic series converges to the natural log of 2, but the harmonic series itself diverges. So now we're going to move into talking about the convergence of a series of functions, because we have the basics down for what a convergent series is, and in general what it means for a series, infinite series of numbers to converge. So now we suppose we have an infinite sequence of functions. Call this g1 of x, g2 of x, and so on and so forth, all the way up to gn of x, and so on and so forth. What does it mean to say that capital G of x is a function of x is equal to the infinite sum from 1 to infinity of gn of x? And again, we're faced with the same problem that we had before. This infinite summation is saying, like saying g1 of x plus g2 of x ad infimum. Right? We add all of the values of the infinite series, or in this infinite sequence together. And we're faced with the same problem as before, in that we have some definitive thing on the left-hand side, just like in this example. We have 1/3 on the left-hand side, and we have this infinite sum on the right-hand side. Only now we're talking about an infinite sum of functions. So just like before, we have that g of x is equal to the partial sum of n equals 1 to some capital N of gn of x plus some error term that we'll try to control. So this is g1 of x plus g2 of x up to some capital Gn of x, some stopping point, plus some error term, En. This term right here is called the nth partial sum. And we're denote this, define this as gn of x. And this term right here is an error term that we can make as small as we wish. So we start out by defining gn of x to be this nth partial sum which we know that we can always do if we have n functions. I can compute the finite sum of those n functions, and this makes a lot of sense mathematically. And the new sequence or the sequence gn of x is called the sequence of partial sums. So the first term in the sequence is g1 of x. The second term is g2 of x, or g1 of x plus g2 of x. Third term is g1 of x plus g2 of x plus g3 of x, and so on and so forth, all the way to infinity. And so what we're going to do is we're going to look into what it means for the sequence to converge. And because of the nature of the fact that each one of these gk's or ggns is a function of x, we're actually going to have two separate types of convergence for a sequence of functions like this. One is going to be much stronger than the other. We're going to start with the weaker type of convergence, which is called pointwise convergence. And pointwise convergence doesn't have all of the nice properties that the other type of convergence has. The other type of convergence is called uniform convergence, and this is going to be very, very important for us in Fourier series. But we want to start with pointwise convergence, which is the weaker form of convergence, but the form of convergence that it makes the most sense to start defining. We'll see an example of this in 1 second, but let's kind of write this down and we'll get started here. So pointwise convergence, or the sequence gn of x converges pointwise to some function g of x if and only if as n goes to infinity of gn of x is equal to g of x for every x in the domain of the sequence of functions. And recall that the definition of the limit is that for every error tolerance, epsilon, and we have to be careful here, we say there exists an integer n that depends on epsilon and possibly on x, such that if n is greater than n epsilon x, then the difference between gn of x and g of x is less than the error tolerance. This is saying that for every point x, we have that the limit of our sequence of functions of x is converging to some value, and that value is exactly the value of the function g of x. A great example of this is going to be the function gn of x is equal to x to the n on the interval I from 0 to 1. And if you think of how this x to the n is behaving on this interval, you know, that x to the 1 is going to be the straight line from 0 to 1. X to the 2 is going to be x squared, x cubed. It's going to look like this, and so on and so forth. But just by taking a quick look at this sequence of functions, we expect that the limit, pointwise limit, as x goes, or as n goes to infinity, of gn of x is going to be the function that is 0 when x is between 0 but not equal to 1, and it's going to be 1 when x is equal to 1. And if we open up a plot, this is exactly what we see. So on this plot right here, we're looking at the function x to the n on the interval from 0 to 1 for various values of n. 1, 2, 3, 4, 5. And I even included a slider here where we can see that as we raise the value from 1 to 2 to 3 to 4 and so on and so forth, we increase the value. Right, this is directly going to exactly the function that I was talking about, which is 0 for x between 0 and 1, and 1 at the point 1. And you can see that right here. So we're seeing that this sequence of functions is converging pointwise to to g of x, where g of x is the function 0 when x is between 0 and 1, and it's 1 when x is equal to 1. And we can go to the definition, right, and even directly show this by saying we'll fix some error tolerance greater than 0. We know that when x is between 0 and 1, we'll need to find some n that depends necessarily on epsilon and on x, such that for n greater than n epsilon x, x to the n minus 0 is less than epsilon. Which we can take the natural log of both sides to get that this is n natural log of absolute value of x has to be less than natural log of epsilon, and because x is between 0 and 1, this is negative. So when we rewrite this, this means that n has to be greater than natural log of epsilon divided by natural log of x, absolute value. So n star needs to be an integer that's greater than or equal to this value. And n epsilon x has to be an integer that's greater than or equal to this value to guarantee that the distance between the function gn and the limiting function is less than epsilon. And on the interval or on the point when x is equal to 1, we don't have nearly as much of a restriction on n epsilon x, because 1 to the n minus 1 is equal to 0, which will always be less than any error tolerance. So there you have it. You can kind of take a look at this plot just to kind of see what this is saying. So if we open up the Desmos window again, and we plot the so n epsilon here, I'm doing the ceiling function of ln of epsilon over x naught, and I'll also plot a little epsilon window here. This is for epsilon is 0.05, as well as I'll plot the value of the function at x naught. Right, so we'll look at whether this is true at the point x naught, 0.5, and you see sure enough, right, the function at 0.5 is within epsilon here. If we change this by making epsilon a little bit smaller, the value of n is going to get larger and larger and larger to make sure that it stays within that epsilon window. We also see that if we change the location of x naught, the value of n will get larger and larger and larger as well to keep up with the fact that you have to stay within the epsilon window here. This is a very neat demonstration because it's showing us that the exact definition of convergence makes a lot of sense. So we want to see, how this relates to what we've been talking about with Fourier series. Like I mentioned before, pointwise convergence is not necessarily the nicest form of convergence that we're going to talk about. There's actually two other much more nicer, more natural ways of defining convergence, but we'll start with pointwise convergence because of the fact that I think it's the most natural starting point. And our first main theorem is directly related to this. And this is actually called Dirichlets Theorem. Which says the following: we assume that f of x satisfies what are called the Dirichlet conditions which are that it is bounded on some interval from negative L over 2 to L over 2, it is piecewise continuous, on the interval from negative L over 2 to L over 2, and third condition is that f of x has a finite number of maxima and minima on the interval from negative L over 2 to L over 2. And if these three conditions are satisfied, then the Fourier series of f of x converges pointwise on the real number line. So for every real number, for every real value of x, not only that, we have that at every point its sum converges pointwise to the average value, the arithmetic average of the left-hand limit and the right-hand limit there should be a u right here. It converges to the average value of the left-hand limit and the right-hand limit of the periodic extension of f. So for instance, if we do the Fourier series expansion of a function from negative L over 2 to positive L over 2, it looks like this. The Fourier series is going to converge to the function that's the periodic extension of this function right here at every single point where it's continuous, and even at the points of discontinuity of the function, you have that it converges to the average of the left endpoint and the right endpoint. So let's say the function looks like this. The Fourier series will converge to this black function, and at the points of discontinuity to the midpoint between the left-hand limit and the right-hand limit. So it'll converge right here, converge right here, they'll converge to this point right here, this point right here, and so on and so forth, at every single point along the x-axis. And this is called Dirichlets Theorem. So I'm not going to go through and prove this, but it's a good exercise to go through and look at the proof of why this actually works. What we want to do is go through, and we've seen a number of different examples kind of done out of the Fourier series. This is the big theorem that kind of governs for us now what conditions f has to have in order to definitively state that a Fourier series is going to converge and what it's going to converge to. Not only that, but it tells you that it's going to be pointwise convergence. We can also use this to show that the speed of convergence, this is a remarkable theorem that I'm going to show first through an example, and then I'll write the theorem down. The speed of convergence of a Fourier series, we've already kind of seen this in a certain way through examples, maybe judge by the behavior of its coefficients. As n goes to infinity. Let's say as capital N goes to infinity. So I guess so I'll use lowercase n here, because just think of these as functions of lowercase n. So the coefficient an or bn is said to be of order 1 over n to the p. Notation for this is sometimes called big O notation, or 1 over n to the p, if the limit as n goes to infinity of an over 1 over n to the p is equal to some constant, which is non-zero. And I want to note here that the same definition applies to Bn as well. So I want to go over a very, very powerful modifying example. Just consider the function f of x is equal to x for x from 0 to 1. You know from before that the even extension cosine series is the function f even of x is the absolute value of x for x from -1 to 1. And the odd extension the extension that gives us the odd function that matches x, f of x equals x on the interval from 0 to 1 is actually just the function f of x equals x itself on the interval from -1 to 1. And when we go through the process of solving for the cosine series, the even extension cosine series ends up being a0 over 2 plus the summation from n equals 1 to infinity of an times cosine of n pi x, where a0 ends up being 1 and an ends up being 2 times -1 to the n minus 1 over n pi squared times n squared. And doing the same process for the odd extension ends up giving us the Fourier sine series, which is the sum from n equals 1 to infinity of bn sine of n pi x. Bn for the sine series ends up being two over pi times n times negative 1 to the n plus 1. And previously I should have had an absolute value here on a of n. But doing this allows us to see that the Fourier coefficients of Bn are governed by this 1 over n right here, so they're decaying at a rate of p equals 1, whereas these ans here are decaying at a faster rate, a rate of n squared. So because of this, right, we expect that the cosine series, the even extension of this function, will converge much faster than the odd extension. And if we open up Desmos to get an idea of what this looks like, this is exactly what we'll see. So this in solid black right here is the function f of x from 0 to 1. The even extension is this dashed line right here, the blue dashed line. And the odd extension is this red dotted line. And so we know from the previous theorem that the even extension, or the Fourier cosine series, is going to converge to this function right here, which is the 2 periodic extension of this even function, whereas the Fourier sine series is going to converge to the 2 periodic extension of this odd function right here. And we've predicted that the cosine series will converge faster because the coefficients have a higher order. They're decaying faster with n. And if we visualize the cosine series here, which is this solid purple curve, and the sine series, which is this solid orange curve, and we increase the number of terms in the Fourier series from 1 to 100, you see very, very clearly that the cosine series converges almost immediately, but the sine series takes a while to get to a point where it's converging. And even right at these points of discontinuity of the function, where the odd extension is discontinuous here, at this point right here, this point right here, the series still isn't behaving very nicely. This is what's known as Gibbs phenomena. So it's that if you have a discontinuity in your function that you're expanding, no matter how many terms you take in the Fourier series still, it'll converge, right, based on the convergence theorem when you have infinitely many sums. But for any finite number of sums at the discontinuity points, you have these spurious oscillations which don't go away. They do, right, kind of, you can see that as you add more and more terms, they get kind of, smaller and smaller, and it's better and better approximated here, but you will always have this oscillation right here, unless you can somehow sum infinitely many terms. This is what's known as Gibbs phenomena. But if we take a step back and kind of just consider maybe the first 10 sums right here, you see that after even 10 sums, the function that's a little bit more continuous, which is the even extension, the Fourier series is having a much easier time converging to the function than the discontinuous odd extension is. This is really, really neat, and actually kind of hints at a deeper theorem going on here, which I'm going to write down now. So we have the following theorem that summarizes this result. So we see that let f of x and its first k minus 1 derivatives satisfy the Dirichlets conditions from before. So both the function f and its first k minus 1 derivatives satisfy those Dirichlets conditions from before on the interval from negative L over 2 to positive L over 2, and assume that the periodic extensions of all of these functions as well so periodic extensions of f of x, f prime of x, all the way up to and including f k minus 1, the k minus first derivative of x, are continuous. This presupposes that fk is the lowest discontinuous derivative. I really want to emphasize here that f is the derivatives of the periodic extensions. Then the Fourier coefficients are at least of order 1 over n to the k plus 1. And one basic remark here, I have two simple remarks. So this means that the smoother the periodic extension of f is, the faster the Fourier series will converge. This is exactly what we saw in that last example. And I also want to say that this is a very powerful theorem. The power of this theorem lies in that we can visually examine a function. Specifically the periodic extension of a function. And determine how fast its Fourier series will converge. This is actually quite remarkable, and sometimes we could use this to choose whether or not we want to use an even extension or an odd extension when we're doing applications. If we require that the Fourier series have a certain level of smoothness. So this covers all of the things we need to know for now about pointwise convergence of a Fourier series. The next type of convergence that we want to define is called uniform convergence, which is a stronger type of convergence that we actually need in order to do term-by-term differentiation and term-by-term integration, which is very, very important for Fourier series, because this is how we go through and show the orthogonality relationships and everything else that we've gone through and been using to this point so far.